All right, let's do something really cool today. We're going to design a distributed key value store right from the ground up. We'll be digging into the exact same principles that power some of the biggest systems on the planet, like Amazon's Dynamo. So if you're a fan of system design, well, you're in for a treat. Okay, so here's our game plan. First, we'll lay the foundation and figure out what we're actually building. Then, we'll draw up the blueprint for massive scale. After that, it's all about protection, building safeguards for availability, bringing in a referee to handle data conflicts, and finally, building a fortress to make this thing truly resilient. Let's get into it. First things first, before we even think about servers or algorithms, we have to define our mission. What is this system supposed to do? What are its core functions? And what promises is it making to the applications that will use it? Look, at its core, the whole concept is deceptively simple. It's basically a gigantic dictionary or hash map, just one that's spread out over potentially thousands of machines. You've got a unique key, and that key points to a value. That value could be anything: a user profile, a configuration file, an image. And the API, it's as simple as it gets. You have get key to fetch data and put key value to store it. That's it. So you might be asking, why on earth would we choose this over a standard traditional database? Well, it's not just about being schemaless and flexible. The real fundamental reason is that we are making a very specific design choice. We are prioritizing massive horizontal scale, the ability to just add more machines, and always-on availability. And to get that, we're willing to relax our guarantees on absolute up to the nanosecond consistency. That trade-off right there, that is central to every single thing we're about to build. Okay, our goals are set. Now for the really fun part. How do we actually build this thing so it can grow from just a handful of servers to literally thousands without the whole system just grinding to a halt? And this right here is our first massive technical hurdle. As data starts flooding in, how do we make sure we're spreading it out evenly? And just as important, how do we spread the workload evenly so no single server gets overwhelmed and becomes a bottleneck? The answer starts with a really elegant algorithm called consistent hashing. Just picture a circle or a ring. We take each of our servers, we hash their IP address or some unique ID, and that hash value determines their position on the ring. Then we do the same thing for a piece of data. We hash its key, find its position on the ring, and then to figure out where to store it, we just walk clockwise around the ring until we hit the very first server. That's its home. Now, this visual here shows the basic idea perfectly, but you see the problem, right? Just by random chance, you could get a really lopsided distribution. Look here, node B gets this huge chunk of the ring, while node A gets a tiny little sliver. This creates hotspots, exactly what we're trying to avoid. Node B is going to be doing way more work than everyone else. That's not scalable. And the solution to this is just beautiful: virtual nodes. Instead of putting each physical server on the ring just once, we give it, say, 100 or 1,000 virtual identities. We just hash its ID multiple times with different seeds. And by the law of large numbers, when you scatter all these virtual nodes around the ring, the distribution smooths out dramatically. It becomes statistically almost impossible for any one physical server to get a disproportionate share of the load. Okay, great. Our data is now spread out nice and evenly. But what happens if one of those servers just dies? A power failure, a network card goes bad, whatever. Our next goal is to make sure our system stays up and running even when parts of it fail. The key here, of course, is redundancy. We achieve this through data replication. We're going to use a peer-to-peer model, which means there's no special master node. Any node can handle any request. To make that work, every piece of data gets copied or replicated across n different servers. N here is our replication factor, and it's something we can tune. A really common choice for n is 3, meaning there are always 3 copies of every single item floating around in our cluster. So how does this replication actually work with our consistent hashing ring? Well, it's pretty slick. The first node that's responsible for a key, node B in this case, becomes the coordinator for that write operation. If our replication factor n is 3, that coordinator is responsible for sending copies of that data to the next 2, or n-1 servers it finds as it walks clockwise around the ring. That group of n nodes is called the key's preference list. Now this is where things get really interesting. In a distributed system of this size, things like network partitions, where some servers can't talk to others, they're not just possible, they are inevitable. And this leads to a huge challenge. What happens when different copies of the same data get updated at the same time, independently? You guessed it, data conflicts. So to resolve these conflicts, we need to understand causality. Which update happened before which? Now you might think, let's just use timestamps. But that's a trap, because clocks on different servers can drift and you get into all sorts of trouble. We need something way more robust. We need vector clocks. Think of a vector clock as a piece of metadata attached to our data that acts like a detailed version history, tracking which node performed an update and in what order. Let's just walk through this. A client writes to node A. The vector clock is A1. It writes again, the clock increments to A2. Now disaster strikes. A network partition separates the client from node A. The client still needs to save its work, so it talks to node B and node C instead. Now we have two different versions of the data with two divergent histories. When the network heals and a client tries to read that key, the system will see that neither clock is an ancestor of the other. It knows they are in conflict. And here's the crucial part. The database doesn't try to resolve it. It sends both conflicting versions back to the client and says, hey, you figure this out. The application is responsible for merging the data into a single correct version. Now, one of the key requirements for a system like this is that it needs to be configurable. Not every application has the same needs, right? Some might need blazing fast reads, others might need rock-solid consistency for writes. One size definitely does not fit all. So how do we let developers tune this behavior? The answer is tunable quorums. So we have n, a replication factor, which is 3 in this example. Then we define two more numbers, w, the write quorum, and r, the read quorum. W is how many replicas must confirm a write for it to be considered successful. R is how many replicas we need to hear from for a read to be successful. The magic rule is R plus W greater than N. Think of it like a Venn diagram. This formula guarantees that the group of nodes you read from, R, and the group of nodes the last write was confirmed on, W, must have an overlap of at least one node. That overlap ensures you will always read at least one copy of the most recent version. And as you can see, by tweaking R and W, we can optimize for fast reads, fast writes, or strong consistency. All right, let's bring it home. We're moving into our final section. And now we're going to build a true fortress, a system that can handle all sorts of failures and stay fault tolerant. So for those temporary failures, a server is rebooting or there's a quick network glitch, we use a really clever trick called hinted handoff. If a node in the preference list is down, another healthy node in the cluster will accept the write on its behalf. It basically leaves a sticky note, a hint, saying, hey, this write actually belongs to that server that's down. As soon as the original node comes back online, the temporary holder hands off the write. This keeps our write availability high even during short outages. Hinted handoff is awesome for brief outages, but what about a more serious problem? What if a server isn't just rebooting? What if its hard drive fried and it's gone for good? Or what if, over a long period of time, the data on different replicas just slowly drifts out of sync? We need a much more robust solution for that. And that solution is a really cool data structure called a Merkle tree. This is one of my favorites. Imagine you take every single key value pair in a certain range and you hash them. Those are the leaves of your tree. Then you take pairs of those hashes and you hash them together to create the next level up. You keep doing this, hashing the hashes, all the way up until you have one single root hash. This one hash is now a compact, cryptographic fingerprints that represents the exact state of potentially millions of keys. Now, the process of finding and fixing these data inconsistencies, which we call anti-entropy, becomes incredibly efficient. Two nodes just need to compare the root hash of their Merkle trees for a given key range. If the hashes match, awesome, they're in sync, we're done. If they don't match, they just compare the hashes of the children nodes and they only walk down the branches of the tree that don't match. This lets them zero in on exactly which keys are different without ever having to send all the data over the network. It's a massive, massive optimization. And finally, how do all these nodes even know about each other? How do they know who's healthy and who's not? They use a gossip protocol. It works pretty much like it sounds. Every second or so, each node picks a few other random nodes and they exchange information, or gossip, about the state of the cluster. This information spreads exponentially fast, kind of like a rumor, allowing every node to build an eventually consistent map of the entire system without ever needing a central server to coordinate everything. So after all of this, it really comes back to one crucial point. Designing a large-scale distributed system is a masterclass in managing trade-offs. You simply cannot have perfect consistency, perfect availability, and blazing fast performance all at the same time. It's impossible. As we've seen with things like our quorum configurations, Every single choice you make is a balance. And knowing which knob to turn for which outcome for your specific application, well, that's the core challenge. And frankly, that's the real art of system design.